All right, so the notes that we are going to do today are on pedigrees, and how we're going to take the notes on pedigrees here is we're going to kind of work through a few together. So we'll do a couple of short worksheets just to understand how do we interpret a pedigree, what are some things that we're looking for, before we try a few out on our own. So we looked at already karyotypes as a way to diagnose genetic disorders, but a pedigree is something else, another tool in our toolbox that we can use to trace family histories, help with diagnosing any types of genetic problems, and to make predictions if there could be possible genetic disorders in the future. So pedigrees are used by genetic counselors to help families that have a very detrimental, harmful genetic condition, and to consult them to give them kind of an idea of what the likelihood is that their child could be afflicted with the disease. Some couples might choose to not have children if they know there's a high likelihood or maybe a guaranteed fact that their child could have a terminal illness, for example. So how a pedigree works, how we interpret a pedigree. So it's used to show marriages, it's used to show offspring, and it's used to show relationships. And we try to get as detailed as possible. So a circle represents someone who is female, and a square represents someone who is male. A line between two people indicates a marriage. And then a vertical bracket, so a line below, indicates children. Now, in this family here, we have 3 children. So notice in the same generation, there's people added outside, but they're not part of the bracket. So these are people that were married into the family. It's broken down by generation. So each level, this would be first generation, second generation, third generation. So grandparents, moms, dads, aunts, uncles, brothers, sisters, cousins, for example. And then you'll see some of these circles and squares are shaded and some are not. A shaded circle or square will indicate that a person is expressing or showing the affliction, whereas one that is not shaded shows that a person is not does not have the trait. These are kind of outlining what we just saw above. You will also see every now and then a circle that will be halfway colored. So in some pedigrees, this will represent a hybrid or a heterozygous genotype. So somebody that carries the trait, but they don't display the trait. They don't have the trait themselves. They're just carriers of it that they could pass on to an offspring. I'll go flipping to our next page here. So a pedigree, it looks just like a family tree, and that's exactly what it is. However, it's focusing on and it's tracing just a specific genetic trait. So it doesn't look at all possible genetic disorders within the family. It just looks at a specific one. And so there's some helpful hints, things to think about when we're analyzing a pedigree. The first is that if an individual is homozygous recessive, so if they're recessive for a trait, then both parents must have at least one recessive allele. So they have to inherit one allele from both parents that's recessive. If an individual shows the dominant trait, then we're going to follow a principle of dominance. So that means they must have a dominant phenotype. And if both parents are homozygous recessive, then that means all offspring will be homozygous recessive because there's no chance to inherit a dominant uppercase allele. So there's many different kinds of pretty detrimental diseases. Others that are maybe not terminal, but just some abnormalities from a normal human karyotype that can be traced using pedigrees. Now we're going to look at a few of these that are listed above here. And they'll either be in this worksheet or possibly in future worksheets. But we have conditions caused by recessive alleles like cystic fibrosis. This is a disease of the secretory glands, including those that make mucus and sweat. Falconia anemia, which is a blood disorder. Albinism, a lack of pigmentation. And then phenylketonuria, which is a metabolic disorder. There's other conditions that are caused by dominant alleles, and so therefore they're expressed in either homozygous dominant individuals or those that are heterozygous. So some examples are those: polydactyl, which is the presence of extra fingers, achondroplasia, which is a type of dwarfism, and then neurofibromatosis, which is a nervous disorder. So we're going to first break down, take a second since we just did a little bit of notes on the front here, analyzing relationships within a pedigree. So we're going to take a second here just to look through that front page again and fill out just 1 through 7. And then we'll resume and we'll walk through 8 and 9 together. So at this point in time, if we can pause the video and give everyone a couple minutes to work through 1 through 7. Okay, so it should be done working through 1 through 7. And so we're going to take a quick peek and check our answers, and we'll go through each one real quick. So C here is pointing to a box. And so C here represents a male. A female in a pedigree is represented with a circle, or A. Line B is pointing to this line connecting A and C. So this represents a marriage. A person who expresses the trait. So expression of a trait, somebody that has the trait, is going to be any individual that has their circle or square shaded. So in this case, the female, or A, expresses whatever the trait is. A person who does not, it'll be left white, so that'll be C, our male. The connection between parents and offspring, so to show you how many offspring a couple has. So this is going to be D here, this line going down, and this bracket extending from D. And then here you're asked how many generations. So that's going to be each level of individuals that we see. So I have 1, 2, 3 generations here in this pedigree. Now, typically with a pedigree, you'll be told, although there might be some that you won't, there'll be some higher level thinking questions later on, but you'll be told generally in the beginning here what the affliction is that we're tracing. So what's the genetic disorder or abnormality that we're tracing, and if it's dominant or recessive. So again, if it's dominant is uppercase letters, uppercase alleles. So anybody with an uppercase letter would have the trait. And then if it is recessive, that would be somebody that has 2 lowercase letters. Then they would have the trait. So we're going to assume that this chart here is tracing the dominant trait of white forelock. So in this case, the affliction is dominant. And what white forelock is a tuft of white hair on the forehead. And so that's actually what this individual has up here. So nothing too bad compared to what we could be tracing, right? So we're asked here, what is the most likely genotype of individual A? So individual A has white forelock. So that means at least one allele is dominant because they have white forelocks. Then the next question is their second allele also an uppercase F, or is their second allele a lowercase f? So I can figure this out by looking at the children. So if this was an uppercase F, then it would be very likely then that all the children would have white forelock. And actually, not very likely, it would happen because if the dad here did not have white forelock, then his genotype is little f, little f. So if this was a big F, then every single child would receive one big F from mom and one little f from dad. And so they would all then be heterozygous, but with white forelock. I have two children that have white forelock, so they got the big F from mom, but I have two children that do not have white forelock. So this would only happen if their genotype was little f, little f. So that means mom here must have a little f to give, so that one little f was given from mom and one little f was given from dad. So this genotype here should be big F, little f, since white forelock is dominant. So what's the most likely genotype of individual C? So if individual C does not have white forelock and white forelock is dominant, then that means their genotype must be recessive, or little f, little f. Otherwise, if they were big F, or big F, little f, then they would have white forelock on their hair. So we're going to try a pedigree on our own, and this time try identifying genotypes. And so the trait that we're going to look for is Falconi anemia. And so in this case, the dominant form is normal bone marrow function. So in other words, no anemia. So for this genetic disorder is recessive. So individuals that have it have slow growth, heart defects, possible bone marrow failure, and high rate of leukemia. So if this is a recessive form, again, to be recessive, that means you have two lowercase alleles. So that means individuals with this disease must just be little f, little f. Now you're told that carriers, so people that are heterozygous for this particular pedigree, happen to not be half shaded. So in some pedigrees, you'll see a circle maybe in half with half shaded, half not. So that would represent somebody that was heterozygous. But again, you're not told of this here. So this does require a little bit more thinking of figuring out genotypes. So I'm going to, again, ask that we pause the video. And we're going to give everyone a few minutes to work through 1 through 5. And again, we're going to be doing this in our seats. This is some quick questions. So if you're super stuck, ask your neighbor. Do also have a key if we really need any help. But take a few minutes to go through 1 through 5. And then once everyone's worked through 1 through 5, we'll resume the video. So hit pause and we'll get going. All right, so at this point, we should have worked through 1 through 5. So we'll take a second to check our responses. So here we're asked about Arlene. So Arlene, the circle here is shaded. So that means Arlene must be little f, little f. And all these people that have shaded circles or squares must also be little f, little f. So it's always good once you kind of know genotypes, anything for sure, it's always good to throw that down because that can help you if you have any like questions or feeling kind of stuck later on in the future. 2, so here we're asked what is George's genotype. So if I look at George, so he is not shaded, so he can't be little f. So now the question is he homozygous dominant or is he heterozygous? So if he was homozygous dominant, big F, then that means he would give an uppercase F to all of his children because that's the only type of allele that he could give. And if these children had an uppercase F, then they don't have a recessive genotype, and so they would not show the disease. So since he has 2 children with this disease, then that means he cannot be big F. He would have to be big F here so that he could offer a recessive allele to 2 of his children. So George's genotype must be heterozygous, big F. Next, we're asked about Anne and Michael. So here, Anne and Michael, they do not have anything shaded. So we know they both at least have an uppercase F. Now the next question is, so are they dominant, homozygous dominant, or are they heterozygous? So we can look at their child, Carla. Carla here has the disease. Her genotype is little f. So if Carla has the disease, that means she must have gotten these 2 little f's from her parents. So we know one of their alleles has to be an uppercase F because they do not have the anemia. So that means their other allele must be lowercase f so that they could offer both of those then to Carla. So Anne and Michael must be heterozygous. So now we're asked about some, most likely situations. So Sandra here. So here Sandra is married to Tom. Sandra does not have anemia. Tom does. So we know that she is at least an uppercase F here. We at least know that allele. So now it's time to try to figure out, okay, what could her possible genotype be? So I'm going to look at her children now. So she had 2 children. Neither of them happen to have the anemia. And if I even continue to trace further generations down, her grandchild does not have anemia. So we don't know for certain because, again, it's principles of probability. So she could be little f and just happened to, by chance, give both of her kids the dominant allele. We don't know for sure. But if we were to pick one based on likelihood here, since neither of her children have it, most likely Sandra marries into the family here and she is homozygous dominant. So she happens to not carry the anemia. Most likely. Now for 5, you're asked to list 3 people other than George who are most likely carriers of the anemia. So as we work through this assignment, we were able to pick out some people. So you've got a few options you could have here. But going through the list, so we're told that Sam is big F little f. So a carrier would be somebody that is heterozygous. So they don't have anemia, but they could pass it on. So they'd have to have a little f in order to do that. We're also told that Daniel is heterozygous. And while working through this worksheet, we find that Alan and Michael should be carriers. Or I'm sorry, Anne and Michael. Okay, and then again, this is posing a likely, so what could possibly happen here? So here for Alan, so Alan does not have anemia, but his dad does. So his dad would have to give him a little f, and since he does not have anemia, he would have to have a big F. So Alan we can throw in this list. And if you have Chris, that's kind of a big maybe. So he I wouldn't necessarily throw down because we don't quite have enough information about Tina. But we do know that he is at least has one up dominant allele, and that he could inherit that from Alan. So it's a possibility, but we don't quite have enough information to know for sure to make it a most likely scenario here. So Chris is like he's a big maybe in this one. It's possible, but we need to know a little bit more about Tina here to know for sure. So we are going to do a few more of these pedigrees later here in a bit. We're also, though, going to start to trace and talk about over the next couple of days, too, a specific type of disorder that are called sex-linked disorders. These you could also kind of trace in a pedigree as well, or we could use Punnett squares, which we'll do here in a second, to help to identify the likelihood of inheritance. Now, what a sex-linked disorder is a disorder found, oh goodness, zoom in here a little bit more. The disorder found on the sex chromosomes. So that means they're found on the X or the Y chromosome. Now, you notice in our karyotypes that the X chromosome happens to be much larger than the Y chromosome. And so because of the size of the X chromosome, not all, but most genetic disorders happen to be found on the X chromosome. These sex-linked disorders, so they can be dominant or recessive. So just like our anemia and our white forelock that we trace, they could be dominant or recessive disorders. Now, males, unfortunately, you happen to have a much higher risk of having a genetic disorder that is found on the sex chromosomes. That's because you only have one X chromosome, and so because of that, if that X chromosome has a disorder, it doesn't matter if it's dominant or recessive, you will have that disorder because if it's dominant, then you have it. And if it's recessive, you don't have another X chromosome to kind of overshadow that. How we talked about with heterozygous carriers, that dominant allele overpowers the recessive, so you don't have a second X chromosome to overpower that. So you do have a higher chance of having a sex-linked disorder. Also, females don't have a Y chromosome, so if there's a disorder on the Y chromosome, then they won't have it. You, unfortunately, also have a Y chromosome. So if it's on the Y, you'll have it. If it's on the X, you'll have it. So males statistically have a much higher chance of having a sex-linked disorder. So a common one that exists in our society, and I figured would be a little fun to introduce these disorders with, is one that is also found in my family, is color blindness. Color blindness, there's a variety of different types. In my family, it's red and green color blindness. But color blindness is a sex-linked disorder in which you have a hard time distinguishing certain colors. And so I have a lot of men in my family that have color blindness. And so I thought it would be kind of interesting to trace my family's history a little bit. We can use a Punnett square to do this, to see what is the likelihood that I could possibly be a carrier for color blindness, since I myself am not colorblind. And what about for my siblings? So in my family, it is on my mom's side where we've inherited color blindness, possibly. I have two siblings, a younger brother and a younger sister. My younger brother happens to be colorblind. He can't see red or green colors very well at all. My sister and I happen to not be colorblind. And on my mom's side, my mom has 8 brothers, and almost half of them are colorblind, and the other half have normal eyesight. On my dad's side, nobody in the family is colorblind. So I know our family is inheriting this color blindness trait from my mom's side. So my mom, being female, has 2 X chromosomes. Now, since my brother is colorblind, that means she must have a X chromosome that has color blindness on it. So we're going to use a superscript here, C, to represent the bad X, the one that has color blindness on it. Now, since my sister and I are not colorblind, that means she must also have a good normal X that does not have color blindness. My dad, being male, has the sex chromosomes XY, and since nobody on his side of the family, tracing back generations, has color blindness, then he should just have a normal X and a normal Y. And we know for certain he has a normal X, because if he didn't, then it'd be much more likely that my sister or I would be colorblind. So what I can do is I can take the sex chromosomes and I can make a Punnett square to see what are the likelihoods of my siblings' genotypes. Sorry, I got an alarm on. Oh goodness. Okay. So my mom's genotype is XCX. So I can put this bad X over one box, this good X over another. And then my dad being XY, so I can split his alleles over on this side. So now I'm going to do my crosses. So I'm going to match up each box. So this would be XC and X. These here would be XX. This would be XC and Y. And this here would be XY. So these are all the possible genotypes for the children of my parents. So doing a breakdown for the girls, so for my sister and I, so there's no chance, looking at this Punnett square here, that Miss Wiesel could have been colorblind. So lucky me. Also means there was no possibility at all either that my sister could have been colorblind. However, there's a chance though that I could have both good X's, or I could have one X that has the color blindness gene on it. So there is a chance Miss Wiesel is a carrier of color blindness. So unless I pay to get some genetic testing done, which I'm not going to spend that kind of money because this is not a disease that's going to be that conflicting for life, right? But so unless I do that or have a few children, there's no way for me to know really if I could be carrying color blindness or not. But I have a 50-50 chance that I could be. Now, as for my brother, here, so my brother, since he has color blindness, his sex chromosomes must be an afflicted X and then a normal Y chromosome. But there was a chance that my brother could not have been colorblind. So just due to unfortunate statistics, he happened to have received that colorblind X chromosome there, but there was a chance that he could not have been colorblind. 25%, I suppose, if you're also including the outcomes of sex, but 50-50 if you're just looking at specifically between the two XY combinations. All right, so that's it for our notes for the day. So you're going to receive now a more in-depth pedigree practice. And so do your best with the practice, and I will be providing answers so you can check your understanding along the way and then email me with any questions. But you'll be receiving that tomorrow. So hope you're all doing well and have a good day, and I'll be chatting with you soon.